Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics courses, you've come to the right spot. So go ahead and hit the subscribe button and then check out some more videos and watch the current one. Let's go ahead and get into this one. I want to take a look at what's called the metric topology, and let's see what that's all about. So let's say, given a metric space, so for a metric space, xd, so x is the underlying set and d is the metric. So for a metric space xd, for an element x in the set x, and for epsilon, which is greater than 0. So for an element of the set x and for a positive value of epsilon, we define an epsilon ball centered on x to be, okay, so for an element of the set and for a positive epsilon, I'm going to define an epsilon ball to be the following. Okay. So the notation, so b dxe, so the ball with respect to the metric d centered at the point x, and then with distance epsilon is going to be the following. It's the elements y in x such that the distance between x and y is less than epsilon. Okay, so it's all the elements in this set whose distance away from x is less than epsilon. In particular, it's visual to see an example, let's say in R2, and let's say my center point is here, and let's say my value of epsilon, which we imagine as a radius, and kind of get out of the way there, so this is x, and then let's say this is, the value of this is epsilon. It's going to be every point that is going to be within that disk here, because if I say this is my point y, then the distance between x and y in that case would be smaller than epsilon, and so therefore this would be my epsilon ball in that case. Now what I do is I'm going to take, for this metric space, the collection of all possible epsilon balls, where epsilon is any positive number, x is any element of the set, and then I'm going to use that, and then that whole collection forms a basis for a topology called the metric topology. So let's go ahead and write that out. The collection of all epsilon balls for x, let's say for xd, so for that particular metric space, forms a basis for a topology which is called the metric topology. So it is the topology induced by that metric. Okay? And let's go ahead and take a look at a handful of examples. All right, first example. Let's see, that green one doesn't really show up well. I think this one shows up pretty good. All right. So for example, let's take the metric space consisting of, so let's say R and then D, where the metric D is, I guess this marker isn't going to last much longer. The distance between 2 points is the absolute value of their distance. So it's just the distance between the 2 points on a number line. Okay? That's the metric that we're going to use. Well, what I want to do is, let's say, what are the epsilon balls in this case? And then let's see if we can describe what the corresponding metric topology would be. Okay? Well, for this metric space, let's describe the epsilon balls. Okay. Well, again, I'm going to say let epsilon be greater than 0, and let's say x be an element of the underlying set. Okay? Well, here's the epsilon ball centered at x with, say, distance epsilon. So b dx epsilon. And this is equal to the real numbers y, so the elements in this set, such that the distance between x and y is less than epsilon, right? This is just straight from the definition. And, well, what can we say about that? This is y such that, remember that in this particular case, my metric was the absolute value metric, so it's the absolute value of their difference, said differently, the distance on the number line, and that would be the absolute value of x minus y is less than epsilon, okay? And, well, for that absolute value, we can rewrite it. Let's see, x was a fixed value, y is the unknown. So let's see if I want to write that as... Yeah, the absolute value of x minus y is the same thing as the absolute value of y minus x. I just want to make sure my sign is the right way. And of course, the metric is symmetric, right? The distance between x and y is the same thing as the distance between y and x, so these two are the same. And then this would give me the set of y such that, now an absolute value inequality can be rewritten as negative epsilon less than y minus x is less than epsilon. And this is equal to the elements y such that y is less than x plus epsilon and bigger than negative epsilon plus x. But notice that this is just an open interval, x minus epsilon, x plus epsilon. Okay. And therefore, the basis elements, the epsilon balls in this particular case, are simply the open intervals. Well, the basis consisting of open intervals in the real line, in other words, all of the open intervals, right, epsilon can be anything and x can be anything, generates the usual topology. So this right here is how I generate the usual topology that we've talked about in many videos. It is actually the topology induced by the absolute value metric. Okay? Let's take a look at some more examples. Before I give another example, let me give a definition, and then we'll do an example after that. So definition: a topological space x tau is, now let me kind of, before I finish the sentence, it's sometimes possible, so if I have a metric, okay, if I have a metric space, I can use that metric to define a topology, right? So I can generate a topology given a metric. What we are now going to briefly discuss is, what about the opposite direction? if I have a topology, is there a metric that would induce that? Okay. Certainly if I have a metric, I can have a topology, but if I have a topology, does it come from, or could it come from, a metric? And that's the concept of this definition, and then I'll do an example after that. So a topological space X tau is said to be, no, the word's not going to fit in there, so I'm going to start it down here, metrizable. Oh, yeah, that would have fit. Whatever. So a topological space is said to be metrizable if there's a metric D on X for which the corresponding metric topology is tau. Okay? So a topological space is said to be metrizable if I can find a metric that would induce that same topology. And let's go ahead and I'm going to take a look at a specific example that is going to show that a topological space that we've referred to throughout quite a few of the videos in this playlist is actually a metrizable space. So the example that I want to show you is the discrete topology on any non-empty set is metrizable. So let's go ahead and establish that. Start from the beginning. First and foremost, if you forgot, the discrete topology means that every single subset is open. So the topology is equivalent to the power set, right? Every possible subset of the non-empty set is open. And I want to show that there's actually a metric that's going to generate that. All right. Well, define. So let's say X is the non-empty set, right? Just so we have a name for it, okay, so I can refer to it. So let's say X is the non-empty set and define the function D, which takes X cross X, so it takes pairs of elements in X, and it returns a real number by, okay, if the ordered pair that I plug into this, first and foremost, it could either be distinct values or it could be the same value. So X, the inputs could be the same or they could differ. And if it's the same function value, so like D of AA, whatever A was going to be 1, otherwise it is 0. And it's a straightforward exercise to verify that this is in fact a metric. So go ahead and can work those steps out, but it's pretty straightforward to show that this is a metric. I'm just going to go ahead and assume that. So define this function by that. Then D is a metric, right? And the epsilon balls for this metric would then generate a topology. Well, let's consider the epsilon balls where, now remember that the value of epsilon is any positive number, so let's go ahead and let's pick something like a half. So let's say consider the epsilon balls where epsilon is equal to 1/2, and let's see what those would consist of. So let's say the ball with respect to this metric of an element x of that set, and the value of epsilon is equal to 1/2. Well, remember, this is going to consist of the elements of the set such that the distance between x and y is less than that epsilon value, so less than 1/2. Now, if I have this x value as fixed, what other elements in this set has distance less than 1/2, or this d value less than 1/2 away from x? Well, the only possible values that I have for this distance function are 0 and 1. You know what? Let's reverse that. It's 0 if x and y are the same, and 1 if it's different. Okay. The only values that are less than 1/2 away would be x itself. So this would consist of the only value where d of xy is less than 1/2 would be, of course, when it's 0, which means that x and y have to be the same, which means that this is going to be the singleton x. So, with respect to this metric, the epsilon balls are the singleton sets, right? And remember that the collection of all epsilon balls is the basis of a topology, and therefore this basis generates the discrete topology. Okay? Hence, a discrete space is metrizable. Look at one last example. So for example, let's say my set X consists of, see that show up? Let me pick a different marker. Let me check it doesn't show up super bright here. Okay. So let's say the set X that I want to consider consists of all the continuous functions on the interval a to b. All right. Remember, this is equal to the set of f, which takes a to b, or takes a to b to r, such that f is continuous. Okay, so this is all continuous functions, real valued functions on the interval a to b. So I want to take this set right here, and then I want to define the function d, which is going to take x cross x to r by, all right, so d is going to take a pair of continuous functions and it's going to spit out a real number, and here's how the function is defined. D of fg is equal to, it's the definite integral from a to b of the absolute value of f of x minus g of x dx. And first and foremost, notice that if I plug in f comma f, the value is 0. Certainly it's symmetric. And then using the absolute value, which has a triangle inequality, we can show that this metric has the triangle inequality as well. So pretty quickly we see that it is, in fact, a metric. So D is a metric. From that metric, we can then construct the epsilon balls around every one of these functions, and then hence induce a topology on this particular set of continuous functions. And therefore, the resulting topology gives what's called a function space. So it's a topological space consisting of the underlying elements in the set are functions, and then the topology consists of sets of functions, right? But anyway, this is a topological space that you will discuss in your real analysis, complex analysis, functional analysis courses. So in other words, mathematical analysis, function spaces come up very frequently. So this is one that you will be exposed to in those courses. Okay. Thank you for watching, and please consider subscribing.